In this video, we'll discuss how to add and subtract scientific notation. When adding or subtracting with scientific notation, you need to ensure that exponents on the powers of 10 are the same. And this is important right here. The exponents have to be the same. This is similar to getting a common denominator when adding or subtracting of fractions. After you add or subtract the decimal values, keep the common exponent and make adjustments as needed. The same exponent is needed to ensure proper alignment of the decimal values. Now what we're going to do is show you what we mean by that. So if you remember back to elementary school, if we had a decimal value that looked like this, what we would do is rewrite this so that the decimals would actually line up like this. So we draw our line here and we want to make sure our decimal values line up, and then of course we would subtract things vertically at that point. Well, since scientific notation looks similar to this, so say 2.5 times 10 to the 5th, and let's say another one is 1.8 times 10 to the 3rd, all of our scientific notation have a decimal value with only one digit to the left. But that doesn't mean that they're lined up, because the exponents are actually movements of the decimal value itself. Therefore, unless the exponents are exactly the same, the decimal values will not be lined up. We have 4.5 times 10 to the 7th minus 2.5 times 10 to the 7th. Well, they have the same exponent. So we're okay with this. We can just go ahead and do 4.5 minus 2.5, and we'll see we end up getting 2, or 2.0 if you want to call it that, times 10 to the 7th power. We notice how we keep the same exponent. That's a lot like working with fractions and common denominators. You keep the same common denominator. So no problem there as long as the exponents are the same. So on this problem here, all I did was change the exponent to a 6. But what I need to do is make both of them the same. So I can make the 10 to the 7th become a 6, or the 10 to the 6th become a 7. My suggestion is to make this 6 become a 7. Make the smaller one be equal to the larger one. So what I'm going to do is bring down my times 10, and 6 plus 1 makes a 7. Well, if I'm adding 1, remember the little staircase effect. Okay, staircase effect. This is the exponent on this side, and this is the direction. If my exponent is going up, my decimal is going left. So I need to move my decimal one place to the left, and I get 0.25. And if you want to put a 0 out in front, you can. And now I can bring down the rest of the problem. Once my exponents are the same, I simply subtract the decimal values. So 4.5 minus 0.25 will leave us with 4.25 times 10, and we keep the common 7. 4.25 times 10 to the 7th. Now at any time, if this value right here becomes bigger than 10 or smaller than 1, you have to then readjust the exponent. When aligned and at their closest point, Earth and Jupiter are 3.65 times 10 to the 8th miles apart. If Earth is 9.3 times 10 to the 7th miles from the Sun, what is the distance from the Sun to Jupiter? So all we got to do is take the distance between the two planets and add the distance between Earth and the Sun, and what we get is the total distance of Jupiter to the Sun. But you'll see the problem is we have an 8 here and a 7 here. So my suggestion is always make the smaller exponent become equal to the larger. So I'm going to add 1 here, so that would be times 10 to the 8th power. Now remember, if I'm adding 1, my decimal needs to move left. So I'm going to call that 0.93 and a 0 if we want. Plus, bring down the rest of the problem. All I got to do now is add the decimal values. 3.65 plus 0.93 gives us a value of 4.58 times 10, and I'm just going to keep the same common exponent of 8. We're going to try another one here that requires an adjustment before and after. We can see that this 6 is smaller than 7, so I'm going to add 1 to it, make that 10 to the 7th power. That's going to cause an adjustment in the left of 0.95 plus, bring down the rest of the problem, and now I'm going to add these together. 9.4 plus 0.95, and that's going to give me 10.35 times 10 to the 7th power. And this is the actual correct sum. However, I have 2 decimal values here, and I'm not allowed to have that. So what I got to do is move the decimal over one more place and call it 1.035 times 10. And if I'm moving this direction, I remember I'm adding to the exponent, so I now have 10 to the 8th power. Couple of notes just to remember: adjust the smaller exponent to be equal to the larger exponent, then add or subtract the decimal values only, and finally you want to keep the common exponent and adjust that exponent if you need to adjust it, as we did in the last example.